Yes, hello class. It's another day that we continue with our topic, chemical families, and the subtopic, halogens. So today we are going to start with electron affinity, and this is the minimum energy that's required by an atom to gain an electron rather than extra electron. So, and this atom must be in a gaseous state, and we have first, and this one is called the first electron affinity. We have the second one, and the third. So, if atomic radius is large, we find that the electron affinity is going to be reduced simply because let me use the 27, 287, 287. Now we have got varying atomic radius here due to difference in the number of energy level. So electron affinity depends on the number of energy level. The smaller the atomic radius, then we find that the higher the electron affinity due to high nuclear attraction. So we find that this electron is strongly attracted to the nuclear, and therefore that means this one can strongly attract an extra electron, and followed by this one here. This one having the largest atomic radius, that means the nuclear attraction in this is reduced, and therefore it means this one has got the lowest electron affinity, and that means it's the least reactive. So electron affinity affects what we call the activity of halogen, and that is a diagram or a table showing electron affinity. As you can see, electron affinity reduces down the group, except for fluorine, which has got negative 322, even though it's a little bit higher. But if you compare fluorine and fluorine, chlorine is higher, which is the second, is higher than fluorine. In normal cases, we would expect fluorine to be having the highest electron affinity. But in this case, fluorine is having a high electron affinity compared to fluorine. But from there, you see that the trend is that electron affinity decreases down the group. But we have one exception in the place of fluorine. Now, why do you think that fluorine could be having this exception? You find that fluorine has the smallest atomic radius, or rather, the atom is very small. So it has a very small atom. So fluorine, what happens here, that since it has a small atomic radius, the incoming electron, which is supposed to be gained, is going to bring repulsion between, is going to contribute to the repulsion between the incoming electron and the already existing atoms of fluorine here. So since there's an repulsion, most of the energy is going to be used to reduce this repulsion, and that's electron is given there. So this energy is required, most of the energy is required to take care of the repulsion that is coming in here. So when that happens, we find that it's going to have the lowest, or rather its energy is going to be reduced. So because of the small atom, we find that most of the energy will be used to overcome that repulsion between the incoming electrons and the already existing electrons. So electron affinity can also affect the stability. So you find that the higher the electron affinity, the more stable the ion. So that means fluorine is being the most stable. Chlorine is the most stable because it has the highest electron affinity, followed by this one, and that's how it's going to be according to electron affinity. Then that's a table that's going to show how different characteristics of halogens. There's the formula, electroconductivity, solubility in water, melting and boiling point. With some of them have already been discussed. Then let's talk about the chemical property. Now, one thing we know is that non-metals, and in this case we are talking about halogens, do not lose electrons. We find that in the outermost energy level, they have 7 electrons. So, for them to lose this electron, it will require so much energy for the outermost 7 electrons to be lost in order to be stable. So, instead of losing, they are going to opt to gain an electron rather than losing that electron. So, ion formation. How do they form ion? Halogens will form ion because they form ion by gaining an electron in order for them to acquire a noble gas electron configuration. During ion formation, we find that energy is released. And if energy is released, that's why if you look at the electron affinity there, the sign there is negative. But you look at ionization energy, the sign is positive because energy is absorbed. But you look at electron affinity, the sign here is negative. So, now, there fluorine gaining an electron to become that, chlorine gaining an electron to become that, then that is how it's going to be. Now, the ability of an atom to gain an electron is the outermost energy level decreases as the size of the atom increases. And I think this is a concept I've already explained. The reason as to why the gain of electron decreases down the group. For example, fluorine we have 2, 7, chlorine is 2, 8, 7, bromine is 2, 8, 18, 7. Yeah. Now you're looking at this. As you go down the group, there's an increase in the atomic radius. And as the atomic radius increases, that means the nuclear attraction also decreases. And when the nuclear attraction decreases, that means the ability of an atom to attract electrons decreases. And therefore, that means the reactivity decreases down the group. So that is so this is an experiment to show reaction between halogen metal, halogens and metals. So this is a procedure, and one portion you should be, or rather one thing you should consider here is that these halogens are very poisonous. And the reaction involving halogens should either be done in a fume chamber or in an open place. So, plus dry chlorine gas over heated ion rule, as shown in the body observation. So, this is exactly what you are supposed to be seeing, or rather, how you are supposed to set up your experiment. And looking at that, that's how it should be. And don't forget to have concentrated sodium hydroxide such that should there be excess chlorine gas that is meant to escape the atmosphere, it should be reacted with concentrated sodium hydroxide there. Chlorine is very poisonous and should not be allowed to escape the environment. So, for bromine and iodine, heat the ion pool in a test tube in which bromine and iodine vapor are generated and passed over the room. And this is how you are supposed to heat bromine, and there how you are supposed to heat iodine crystals. So that is how you're supposed to set up your apparatus in the laboratory. How you're supposed to do the heating. Now, the reaction between ion and halogen always results into two things, or other one thing, sorry. Reaction between ion and halogens, take the general is ion, plus halogen should give you a salt. Iron plus halogen should give you a salt. So, and the one I want to begin with here is chlorine. Chlorine is the most reactive according to what we are going to use here. If we use chlorine outside, chlorine is the most reactive, and when it reacts, it's going to give us iron 3 chloride. So it's a dark brown crystal, and it's going to give us iron 3 chloride. Then bromine also is going to give us iron 3 bromide. Well, iodine, if we react iron and iodine, is going to give us iron 2 iodide. Iodine, among those halogens, iodine is the only one that is going to give us iron 2 iodide. This is because iodine is not just reactive enough to give us iron 3 iodide. So you find that chlorine will give us iron 2, 3 chloride, bromine will give us iron 3 bromide, but when it reaches to iodine, iodine is going to give us iron 2 iodide. So that's a very important concept that you should be noting. Now, this is the chemical equation, both the chemical and the word equation. Iron plus chlorine give us iron 3 chloride. Then there is the balanced equation there, shown there. Then next, we are going to have bromine plus iron give us iron 3 bromide. Then iron plus iodine to give us iron 2 iodide. Sorry, it should be iron 2 iodide, not bromide, 2 iodide. Now, then zinc plus chlorine should give us, similarly zinc can react to give us zinc plus chlorine to give us zinc chloride. Then zinc plus bromine, zinc bromide. Then zinc plus iodine, zinc iodide. Now, other salts that are formed like this are magnesium chloride, diamond chlorine, ion of aluminum chloride, and sodium chloride there. The reaction between chlorine and metal is more vigorous than that of bromine. And you can understand because chlorine has the more appetite, rather than the highest affinity of gaining electron compared to the one which are being formed here. And the reactivity, order reactivity of halogens with metal increases down the loop. As I explained, the reasons why this one, as you go down the loop, is increased nuclear attraction. And if that nuclear attraction is reduced, then the ability to attract the outermost electron is also reduced. So that's how to focus on. Now, the next part is how do halogens react with water? How do halogens react with water? Now, you are supposed to bubble chlorine through water in a conical flask for a few minutes. Then you are supposed to arrange the apparatus as shown below. Then you are supposed to observe the color of the resulting solution. Then test the solution with litmus paper. Now, when that happens, so this one is going to begin by a production of what we call chlorine gas. And remember that when you are producing chlorine gas, there are two ways of producing chlorine gas. The first one, we're going to use concentrated hydrochloric acid on potassium manganate 7. That's the first part. The second way you can produce chlorine gas is by using concentrated hydrochloric acid on what we call manganese 4 oxide. But remember, whenever you are supposed to use manganese 4 oxide, then the heating process has to be involved. So there has to be some heating for you to do that. Now, for this experiment to take place. So then, after having this setup, and remember that we have specific sodium sodium hydroxide there for the chlorine, for sodium the chlorine, excess chlorine. Now chlorine dissolves in water. We said sodium hydroxide. So you find that the reasons why we have it there, after the chlorine has dissolved in water, any excess chlorine that escapes is going to be trapped inside that constituent sodium hydroxide. So the one we need is the one which is going to dissolve in this way. But after that, anything that is going to be extra has to be absorbed. And remember, as I said, that chlorine is very poisonous. Now, chlorine dissolves in water. And when chlorine dissolves in water, it's going to form two substances, or two products. The first product is called hydrochloric acid. The other one is called hypochlorous acid, or you can also call it chloric 1 acid. So these are two acids that are going to be formed when you dissolve chlorine in water. And after that has happened, so this is actually the equation that's supposed to show the two equations, the two products. Chlorine plus water is going to form hydrochloric acid plus hypochlorous acid, or chloric 1 acid there. Now, when chlorine water is tested using blue litmus paper, we know that chlorine, what are the samples you should know? Chlorine is acidic. And therefore, for you to know whether it's acidic, if you put red litmus paper, it will be red. But now if you put blue litmus paper will first turn into red, showing that that chlorine water is acidic. After showing that the chlorine water is acidic, the next thing that's going to happen, the blue litmus paper is going to be discolorized. In other words, it's going to be bleached and turn white. The reason as to why, and it has to happen immediately. Bleaching action is due to the presence of chloric 1 acid, which is HCl. For some books also you find the writings like that. So whether you meet this one, whether you meet this one, all of them acceptable. Most of the books write it as the upper part, but some of them might decide to write it HOCl. So that is what brings out the bleaching action in chlorine water.